In this video, we'll take a look at how much speculative decoding is going to increase the expected number of tokens generated per one target LLM call. Normally, when we only have one LLM, right, we get one token per one decode step. But in this case, we already ran the approximation LLM gamma number of times. So we might actually accept more tokens per one target LLM call. But how much is the increase approximately? Is there going to be an increase even when we use a really bad LLM, really bad approximation LLM? Are we simply going to waste time rejecting things? Um, or are we actually going to do something good? So that's this section here. And to be able to answer that question, we are first going to see a few definitions. We first introduced this divergence dLK P, Q, which is defined as follows in definition 3.2, where M of X is actually the average of P of X and Q of X. Let's try to understand why lemma 3.3 is true. dLK P, Q is equal to P of X minus P of X plus Q of X by 2. That's actually equal to P of X minus Q of X by 2. Okay, so we got onto this part here. Now after this, we simply add and subtract P of X plus Q of X. Okay, so that's, and then we separate terms. So sigma X P of X plus half sigma X Q of X minus P of X plus Q of X minus mod P minus Q by 2. So that's this part here. And we see that this term becomes 1. 1 minus half of sigma X P of X plus Q of X minus this value here, right? And really when P of X is greater than Q of X, then this comes out of the absolute value as is, and the resulting term is going to be 2Q of X. So when P of X is greater than Q of X, we have 1 minus sigma X Q of X, and vice versa. And you can simply rewrite this like this. Okay, so we have seen why lemma 3.3 is true. Okay, now let's try to look at corollary 3.4. And it basically says that dLK P, Q is a symmetric divergence in the interval 0, 1. And when this divergence is 0, that basically means that P equals Q. Sorry, when P equals Q, you can directly see that dLK is 0. But when dLK is 0, can we show that P equals Q? So sigma x minus P of x modulus of P of x minus Q of x by 2 is equal to 0. What can we say about P of x and Q of x? So that's the question here. And now each term here is a positive quantity because of the absolute value. And the only way in which this entire sum is going to be 0 is when P of x is equal to Q of x for all x. And so that is like both sides of this first statement. When P equals Q, we can immediately see that dLK P, Q is 0. When dLK P, Q is 0, we can also see that P equals Q. Coming to the second part, this is the more interesting part here. So dLK equals 1 basically means that P and Q are having disjoint support, or they're like very distinct probability distributions. So why is that? If you are going to equate this to 1 here, these ones cancel, and we are left with sigma x min P of x comma Q of x is equal to 0. And now again, each of these terms is a positive quantity, and we are adding a bunch of positive terms and saying that uh, all of these terms are greater than or equal to 0 rather, and we are adding all such terms and saying that their sum has to be 0, which means that each term has to be 0. So min P of x comma Q of x is equal to 0 for all x. Now this can take one of these cases. So case one is when P of x is 0, Q of x is not 0. Case two is when Q of x is 0, P of x is not 0. And case three is when both of them are 0, right? So you can see that this basically means that where the probability of the tokens predicted by the P distribution is high or is non-zero, that's where the Q distribution thinks that it is 0. So they're having like a pretty much disjoint support, and that looks as follows. So this is the P of X distribution. If you can think of P as a discrete distribution for a moment, these are all the um, so this is X and the Y value is P of X, and all of these points are the probability values. And if you can think about how it's going to be for Q of X, then because they're disjoint, right? So that is Q of X. Okay. So the corollary basically 3.4 basically tells us that if P and Q are the same, then the symmetric divergence is 0. But if P and Q are pretty dissimilar, then the symmetric divergence takes its highest value, which is 1. Now, let us define a term called as acceptance rate beta here. Now, beta is basically at any given time step t, the probability that a token predicted by the approximation LLM is accepted by the target LLM. What is that probability is beta. The probability that a token is predicted by the approximation LLM is Q of X, right? And then it further has like two possibilities. It is multiplied with 1 if P of X, sorry, Q of X is less than or equal to P of X, or P of X by Q of X if Q of X is greater than P of X, right? So the probability that you predict a token times the probability that it gets accepted summed over all the possible tokens is basically what beta is. Okay? And that is exactly what is defined here. The following quantity here, expectation of X sampled from Q of X, um, minimum of 1 comma P of X by Q of X. Now, why is that true? Because if you take a look at this, right, when P is greater than Q, then the ratio P of X over Q of X is greater than 1. So when P is greater than Q, you're going to get a 1 out of this output, which is this term here. And you're also going to get the ratio itself when P of X over Q of X is less than 1, which basically means that P of X is less than Q of X. So this min here variable captures this if condition here, and therefore beta can be written like this, and this can be further written as follows times. And when you actually write this and you take this Q of X inside the minimum, it's a positive quantity and you can take it like that, then it basically becomes min Q of X comma P of X, right? We can very easily see that beta equals 1 minus d LK P comma Q. So the symmetric divergence that we have defined earlier comes into use when we have this semantically loaded definition of beta. Beta is the probability that any given token is accepted by the target LLM's distribution when we sample the tokens from the approximation LLM. So that is beta here, and it's called as the acceptance rate. Now, if we think about it, the what does beta depend on? Beta depends on how closely the approximation LLM and the target LLM's output distributions match. Now, if they match exactly perfectly, right? So if P equals Q, then beta equals 1, right? Which basically means that the acceptance rate is 100%. We are basically using the same model for both the approximation and the target LLM. Now, that we're not going to do practically because it doesn't make sense. But in that case, beta equals 1. When P is extremely dissimilar and support of P intersection, support of Q is a null set, that is when beta equals 0.
All right. So the acceptance rate when P and Q are extremely dissimilar distributions is equal to 0.
We are going to further define another term called as alpha. Now, this beta here, which is the acceptance rate, it depends on the model, right? Um, so it depends on Q and P, but it really also depends on the context of the sentence for that particular time step. The dog is sitting, and we are trying to predict a token both by um, MQ as well as MP. Now, we know that MQ is like a much smaller model, so it's going to be bad. But the task at hand here is so easy that MQ can also get it right, as well as MP. So this is a situation where the context is so simple that a minimal language understanding enables us to have acceptance of the token predicted by the approximation LLM. Now, if we think about another situation, another context. Now, if this is what we are asking MQ and MP to predict, the word here is more complicated than predicting a proposition. This here is a proper noun. This could have been states, this could have been Arab Emirates, this could have been United Airlines, whatever. All of these are possibilities here, which could be very well be inferred by the bigger LLM, but they might not have, the smaller LLM might not have done well. Now, these are the situations when the token that is predicted by the approximation LLM doesn't make sense, and we really would like the target LLM to step in. That is really the intuition behind speculative decoding itself, where we think that we are going to have acceptance in cases where the context that is given for the next token prediction is simple enough. And we are going to have a rejection when the context is hard and we would like the larger LLM to step in. So beta depends not just on the selection of models P and Q, but also on the context at that particular time step. So if we fix models P and Q, beta is still a random variable uh, for any given time step, right? So we have beta 1, beta 2, and so on until beta gamma, right? All of these are values of the random variable beta itself, and the randomness lies in the context now. We are defining a new term here called as alpha, which is the expected value of the acceptance rate across time steps. That is a solid definition here. And if you have a high acceptance, if you have a high acceptance rate across all the time steps, right, then we can very well say that we are generating more tokens per time step than we would have if we had used only the target LLM. Now, with this definition here and plugging in the definition of beta from theorem 3.5, we can arrive at corollary 3.6. We are now in a position to calculate the expected number of accepted tokens. What is theoretically the maximum number of tokens that we can generate from one speculative decoding step? If we generate gamma tokens from the approximation LLM, it's gamma plus one, right? So all the gamma tokens were accepted, and additionally, we sample one token afterwards from MP's distribution. So let us define gamma plus one indicator variables, I0, I1, and so on until I gamma, where each indicator variable ik is equal to 1 or 0. Ik is equal to 1 if kth token exists. That basically means that the total number of tokens is equal to I0 plus I1 plus and so on until I gamma, right? So notice that this indicator variable is random. The probability that the ith token exists depends on the acceptance rate, right? So if a particular token at any given time step was not accepted, all the subsequent indicator variables from that time step on will also be 0. So n here, the expected number of tokens is actually a random variable, which is a sum of these gamma plus 1 indicator random variables. Now, the expected number of tokens is actually equal to the expected number of the right-hand side, and by linearity of expectation, we get the following. The expectation of an indicator variable is the probability that it takes the value 1. So probability of I0 equals 1 plus probability of I1 equals 1 plus and so on until probability of I gamma equals 1. So what is the probability that the first token exists? The first token always exists, right? So even if no token from the approximation LLM were was accepted, we'll still go ahead and sample one token from the target LLM, right? So the probability that I0 is equal to 1 is 1, okay? What is the probability that the first token um, exists? The probability that the first token exists is the probability with which it is accepted, which is basically equals beta 1, right? What is the probability that the second token exists? It is the probability that the first token exists times the probability that the second token exists. So, and so on until we have beta 1, beta 2, beta gamma, right? So the expected number of tokens depends on the acceptance rate for uh, that particular time step, along with the acceptance rates for the previous time steps. Having betas in this way is maybe not very insightful, and therefore we would like to make an approximation. These betas need not be the same value, right? Because as we had discussed previously, the context uh, heavily influences what the beta value is for a given time step. However, for the sake of simplifying our calculations, let us assume that beta is the same across all time steps, and it is the average value of all the betas. So let alpha is equal to the average value of beta be the acceptance rate for all time steps. Okay, so this is an approximation that we are making so as to simplify our calculations, which basically implies that the expected number of tokens is 1 plus alpha square and so on until alpha power gamma, right? And so this is actually equal to 1 minus alpha power gamma plus 1 by 1 minus alpha. This geometric progression sums to this. Okay, so this is the expected number of tokens. We can see that the denominator, so alpha is a value between 0 and 1, right? It's an expected value of beta, which itself is a value between 0 and 1. So alpha is going to be between 0 and 1. Any power of alpha is going to be smaller than itself. So the numerator is always going to be smaller than the denominator, and the expected number of tokens is always going to be greater than or equal to 1. So E of n is going to be greater than or equal to 1. It's going to be 1 in the case when alpha is 0, and it's going to be strictly greater than 1 for any other alpha, no matter how small it is. So we initially asked the question, well, even if we use an extremely bad LLM for trying to predict tokens in speculative decoding, are we still going to have a speed up? And this formula here promises that we are going to have a speed up no matter what when alpha value is non-zero. This, these are the excerpts from the paper. This graph and this excerpt is from the paper itself. And so here we can see that for very large acceptance values, we can get a large number of uh, extra tokens, whereas for smaller acceptance values, we can get a smaller number of extra tokens. Just to summarize, right? So for one LLM call of the target LLM, we are generating 1 minus alpha power gamma plus 1 over 1 minus alpha number of extra tokens. This quantity is greater than or equal to 1, and which basically means that we are generating more tokens per LLM call, per target LLM call. If we had only used the target LLM alone without using it in speculative decoding, we would have only gotten one token. So clearly, this method theoretically promises us with more number of tokens if the acceptance rate is good enough. Now, we might actually think, well, what is the, so this is the number of extra number of tokens that are being generated, right? But what is actually the speed up in terms of wall time? So that is this excerpt from the paper here. And let's understand the small variable here. It's called as C. So C, the cost coefficient, is the ratio between the time for a single run of MQ and the time for a single run of MP. So C is basically C equals time MQ by time MP, which is going to be less than 1, right? So C is basically the how fast, uh, what is the fraction of the time MQ takes for running, um, when compared to the time that MP takes. So with after defining C, we can now look at the total wall time improvement factor, and that is equal to 1 minus alpha power gamma plus 1 by 1 minus alpha times gamma C plus 1. Okay, so that is the total wall time improvement factor. So here we can see that there's a trade-off between acceptance rate and wall time improvement, right? So intuitively, if we use a decent sized model in speculative decoding so as to be able to accelerate a bigger model, the smaller model itself might take a decent amount of time. While the acceptance rate is going to increase, the time is also going to increase as well. And we can see that from this relation here. So the coefficient, the cost coefficient sits in the denominator of the total wall time improvement. This, the term, the expression in this box here is the factor by which the total wall time improves. And as you can see, if C increases, this factor decreases. And C increases when the MQ, size of MQ, also increases. But when size of MQ increases, alpha increases, right? So to be able to increase alpha, maybe we would need a bigger MQ. But having a bigger MQ might actually reduce um, the expected wall time improvement factor. So for speculative decoding, we can keep this formula in mind while selecting a model. It need not be too small for because when it's too small, we get poor alpha values, but it need not be too big as well, because then we will not get a very good improvement in um, wall time. An interesting, before we move to the next section, an interesting point that the paper mentions with regards to this expected number of generated tokens is that transformer models are fairly complex models when which try to model natural language. We also have like extremely simple models such as n-gram models, right? So theoretically, even if we use n-gram models with extremely less alpha values, we might still end up getting more tokens per target LLM call. So that's a suggestion that's made in the paper. Uh, and they perform experiments too by having an n-gram model for MQ instead of a transformer, which also surprisingly, or maybe not so surprisingly, yields uh, results that are better than running MP alone.